reason why would you introduce such numbers. And the first thing I do this morning is starting from a question. The question is, consider this equation, and the question is, how many solutions? Okay. Don't be shy, answer this question. How many solutions for this question, for this equation? Can you see it? Can you see the board? Yeah. You told me. How many solutions for this?
One.
Yes, someone says one solution, okay? You probably think about the solution x equals -1. Are you okay with this? Okay, so why I'm asking this solution to introduce complex numbers? Because actually the answer to this question is it depends. Depends on what? Because if I'm looking for solution in n, where n, everyone knows that n is the set of natural numbers. Are you okay with this? If you have questions on this, ask me. Set of natural numbers, by the set of natural numbers, I mean 0, 1, 2, and so on. In n, this equation has how many solutions? In the set of natural numbers, if you look for solution of this equation in the set of natural numbers, you won't find any solution of this. Are you okay with this? So in n, it has no solution. Why? In z, as your colleague said before, in z, where by z I mean the set of natural numbers along with the negative numbers. So 0, 1, but we also have -1, 2, -2, 3, -3, and so on. It has one solution. Okay, the solution x equals -1. Are you okay with this? So the answer is it depends. In n, it has no solution. In z, it has one solution. Okay, so the number of solution of an equation depends on the set where I'm looking for solution. So the same holds for. Okay, any question up to this point? Okay, can I go on? If you have question, please stop me. So, okay, so the link with complex number is in this. The next step is I consider the equation x plus 1 equals 0. I told you how many solutions. You answered one solution. Okay, one solution in z, where you are looking for solution in z. No solution in n. Okay, so one of the way you consider the set of numbers is asking yourself, how many solutions does this equation have? So the same for the equation 2x plus 3 equals 0. This has no solution in n, no solution in z. It has one solution in q. X equals minus 3 over 2. Okay, this is a solution in q, where q is the set of rational numbers. And so on. So let's ask ourselves how many solutions for this equation. Okay. The answer is no solution in R, the set of real numbers. the set we are accustomed to work with. But if you want to extend this set of numbers, you can find also solution for this equation, okay? And we will see that this equation has two solutions in C, where C is the set of complex numbers. Okay, we will see in the application that often it is important to know how to solve an equation like this: x squared plus 1 equals 0. And this has no solution in the set of real numbers, but it has one solution, two solutions in the set of complex numbers. Okay, so we want to extend the set of real numbers. And how to do it? The idea is adding one number more, okay? The imaginary unit, okay? To pass from R to C, we introduce this number. This is called the imaginary unit. I stands for imaginary unit. And this is a number, it's a new number, it's a number that doesn't belong to R, okay? But it belongs to C, okay? And we will see how to build up C. This number has one property, this property. The property is that I squared is equal to -1, okay? This is the basic idea to introduce complex number, okay? Once you have this idea, you have all the complex numbers, okay? So we add to real numbers a unit, a number I, such that I squared is equal to -1. Once you have this imaginary unit, you can solve also equation like x squared plus 1 equals 0, okay? Because since I squared is -1, I can be a solution of this equation, okay? If I replace x equals I, okay, this is a solution of this equation. Are you okay with this? Because I squared is -1, so I squared plus 1 is 0, since I squared is -1, and -1 plus 1 is 0. Okay, and this is one of the solutions of this equation. But I told you the equation has two solutions. So what about the other one, the other solution? One solution of this equation in C is I. Are you okay with this? Any questions up to this point? Okay. The fact is, okay, the basic point is, this equation has no solution in R, so I'm extending the set of real numbers with the set and introduce the set of complex numbers, okay? This is a superset with respect to the set of real numbers. How to do it? By introducing an imaginary unit. And this imaginary unit is another number with this property, the property that I squared is -1. So I can be a solution of this equation, because I, if you replace I in x, you got -1 plus 1, and it is 0. But this equation has also another solution. Which one? Right. Try to answer this question. It's related to I, okay, strictly linked by I squared is -1. The same holds for -I. Okay. Also, negative I squared is negative I times negative I. Minus times minus is plus, so plus I squared. And we already know that I squared is negative 1. Are you okay with this? So this equation has two solutions, I and negative. Okay. So introducing complex numbers means adding two real numbers, adding two real numbers, this imaginary unit. Okay, so a complex number, z is a complex number if it has this form. It can be a real number, a, okay, because every real number must be one of the complex numbers. Okay, as I told you, C is a superset. Okay, C must be a superset of R. Okay, so every real number must be a complex number. So a complex number is made up of two parts. A, the real number, plus I, the imaginary unit, times B, where B is another real number. Okay, so it's not just I that it is the imaginary unit is a complex number, but also 2I, 3I, negative 3 times I, or square root of 2 times I. All these are complex numbers. Okay, so a complex number is made up of two parts. One part, it is called the real part. Okay, Re of Z, the real part of Z. And another part, this one, B, I am of Z, I'm of Z, the imaginary part. Please notice that both the real part and the imaginary part are real numbers. Okay? So it's made up of two real numbers, A and B, the real and the imaginary part. The first one, it's on its own, okay, A. The second one is times the imaginary unit. Any questions up to this point? Are you okay? Are you there? Can you hear me? Please ask me. Answer me.
Yes, we can.
Okay, thank you. So let's go on. If you are okay with the definition of complex numbers, we can see how to deal with operations with complex numbers. For instance, the sum and the product of complex numbers. So the sum and product in C, in the set of complex numbers. How to deal with it? So, okay, it's just a matter of algebraic computation. Okay, if we pick two complex numbers, Z1 equals A1 plus I times B1. This is one complex number. And another one, Z2, A2 plus I times B2. Okay. You can add these two numbers. Okay. Getting the sum. It's simply the addition of the two complex numbers. It's just a matter of algebraic computation, as I told you. Since this is A sub 1 plus IB1 plus A sub 2 plus IB2. Okay. Okay, of course you can rewrite this, okay, by collecting I, the imaginary unit, just to okay, collect the real part, A1 plus A2, and divide the real part by the imaginary part. Okay, collecting I get by B1 plus B2. And this is the sum. Any questions on this? Okay, it's very straightforward. The product, even for the product, we have just to compute the product of two algebraic expressions like A1 plus IB1 times A2 plus IB2. Okay, and this is the product, and in order to have the final expression with the real part separated by the imaginary part, we have to compute the product. Okay, of course, in computing the product, you have to recall the basic property of I. When you compute I times I, don't forget that this is equal to -1. Okay, this is always the basic fact, the only thing, the important thing about complex numbers. So you can try it by yourself, and computing the product of two numbers, you got A1 times A2 plus A1 times IB2, I A1 2, plus IB1 times A2, plus I squared, okay, I squared is -1, B1, B2. So, since I squared is -1, the last one turns out to be a real number. So, if we want to collect the real numbers, we got A1, A2 minus B1 and B2, okay? This negative sign comes from this A squared, okay? This is -1. Plus, let's collect I times A1 B2 plus A2 B1. Okay, so this is the product of two complex numbers. A1 A2 minus B1 B2 is the real part, plus I, the imaginary unit, times A1 B2 plus A2 B1 is the imaginary part. Are you okay with this? Okay, just to check, try it by yourself with a couple of exercises. Z1 is 2 minus 3i, and Z2 is 3 plus 4i, and try to compute Z1 plus Z2 and Z1 times Z2. Okay? Try it by yourself. Okay, and in a few seconds, I will check the answers. Okay, so first one, you have to add the real part, so you get 5, okay, as real part, plus I times 1, minus 3i plus 4i is 1. So the sum of the two numbers is 5 plus I. What about the second? You have to compute the product, 2 minus 3i times 3 plus 4i. You have 6 plus 12 is 18, is the real part. What about the imaginary part? It is -1, okay? Since we have 2 times 4 is 8, minus 9, okay? So -1 times I. And this is the product, okay? Are you okay with this? Any questions? Did you compute it? Okay, so if everything is okay, we can go on with the next step. The next step is introducing the conjugate of a number, okay? The complex conjugate. Okay, what I mean by the complex conjugate, if I consider Z a complex number, its complex conjugate is Z overlined, and it is simply the same complex number with the opposite sign between the real part and the imaginary part. So not A plus IB anymore, but A minus IB. This is the complex conjugate. Okay, complex conjugate of Z. Okay, this number turns out to be very important in many applications. One application is this one. If you multiply Z times Z conjugate, you see, okay, try it by yourself, what happens? A plus IB times A minus IB. So you have, as before, A squared, okay, plus minus IBA minus IB plus IBA plus I minus I is minus I squared. And since I squared is -1, minus -1 is plus B squared. Is everyone okay with this computation? It's the product as before, okay? It's the product. A times I, A times negative IB is negative IAB, IAB, plus IAB, okay? And plus times minus is minus, I squared is -1, so minus -1 is plus B squared. Okay, please notice that negative IAB and plus IBA cancel out. Okay, so the product Z times Z conjugate gives you A squared plus B squared. And it is a non-negative real number. This belongs to Z. Okay, and with this number we can define the modulus. Okay, the modulus of the modulus of a complex number that is like the distance from the origin you saw in the R2, okay, in the Cartesian plane. Okay, so what is the modulus of a complex number? It's like the norm, okay, in R2, and it's simply the square root of Z times Z overlined, and it is the square root of A squared plus B squared. This is the modulus of a complex number. Of course, it has a geometrical meaning. Okay, why? Because we can represent. Okay, so anticipate something on this. But I think that it can be useful to consider the modulus in geometric terms, because if you represent if you consider the representation of Z of a complex number in the Cartesian plane, okay, and you will see this also on the slides, okay. If you represent this number, okay, in the Cartesian plane, so we consider two axes, the x-axis representing the real part, of Z, and the y-axis representing the imaginary part of Z, okay, then you can represent any complex number Z equals A plus IB with a couple of numbers, A, the real part, and B, the imaginary part. So you have a point in this plane. Is it sometimes it's called the Arnhem-Gauss plane, okay, since Gauss is one of the first mathematicians that represents the complex number on the plane, okay. So I can consider this point like Z, A plus IB. And if you want, this is like a vector. It's vector whose components are A and B. So what is the link between the modulus and this representation? It's simply that the modulus is the length of this vector. Are you okay with this? The length of this vector is the square root of A squared plus B squared, is the Pythagorean theorem. Are you okay with this? So, an application of the conjugate is the modulus. What is the modulus? Is a real number attached to the complex number. By taking the square root of the z times z over line, z times its conjugate is equal to A squared plus B squared. Taking the square root of A squared plus B squared, we get the modulus. And this modulus has a geometrical meaning. It's the length of the vector that represents a complex number on the Cartesian plane, on the Gauss plane. Are you okay with this? Any questions about this?
No, it's clear.
Yeah. Okay. Thank you. So, an example, just to be sure that everything is okay. We consider Z1 to be the number 2 minus 3i, and Z2 to be 1 plus I. And we want to compute Z1 times its conjugate and Z1 times the conjugate of Z2. Okay, so try it by yourself. It's a very easy task, but you can try it by yourself just to be sure that everything is okay about complex number, conjugates, product, and all the stuff we saw up to this point. Okay, I begin to write down the solution. The first one is Z1 times its conjugate, okay? So it's like the modulus squared, okay? It's just another way to rewrite this. And this is A squared plus B squared, okay? A1 squared plus B1 squared, where A1 and B1 are the real and the imaginary part of Z1. So A1 is 4, and B1 is negative 3 squared, okay? So negative 3 squared is plus 9. So this is 13. What about the second one? It is 2 minus 3i, so Z1, times the conjugate of Z2. Since Z2 is 1 plus I, its conjugate turns out to be 1 minus I. Okay? And you can compute the product 2 plus 1 minus 3. Okay, so negative 1. And what about the imaginary part is minus 2i minus 3i. So minus 5i. Okay, so these are the two solutions. 13 from the product Z1 times Z1 conjugate, and minus 1 minus 5i for the product Z1 times the conjugate of Z2. Okay, if you have questions on these exercises, please ask me. Otherwise, we can go on with the next step, still using the conjugate. We can compute the ratio, okay, since we computed the sum and the product, okay, but we leave apart the ratio of complex numbers. So what about the ratio of two complex numbers? Okay, as before, we pick two numbers, Z1, A1 plus I, B1, and Z2, A2 plus I, B2. And we want to compute the ratio Z1 over Z2. Okay, so this is simply A1 plus I, B1 times A2 plus I, B2. Okay, but this expression is not very useful, since from this expression we can't say which one is the real part and which one is the imaginary part, because let me write just this. We don't know which one is, we don't have this form, A plus IB, okay? Which one is A and which one is B? Because we have I in the numerator and also in the denominator. So it's not good. This form doesn't work. So we can use the complex conjugate to turn to another form. Okay, it's like the rationalization of the denominator. Okay, we multiply in order to get a formula like A plus IB. We multiply both numerator and denominator times the conjugate of the denominator. Okay, so we multiply this ratio times A2 minus I times B2. Okay, this is the conjugate of the denominator. We can do it if we multiply both numerator and denominator. Okay, when you compute an algebraic step, okay, like this, you have to ask yourself two things. Can I do it? First thing. And is it useful? First question, first answer is yes, we can do it, because we are multiplying both numerator and denominator times the same number. So we can do it. The second answer is yes, it is useful, since multiplying the 8 2 times plus IB2, so Z2 times its conjugate, as you know, I recall you that this is A squared plus B squared. So you don't have I anymore if you make this computation. So what happens in the denominator? We have A2 squared plus B2 squared. Okay, since as before, A2 minus IB2 plus IB2 A2 cancel out. So we get just this, the modulus squared. Okay, and what about the numerator? The numerator is simply a product, okay, as before. So A1, A2, plus I minus I, B1, B2, it is negative I squared, so plus, okay, plus B1, B2. Okay, so plus B1, B2. Okay, the first part of the product of the two numerators. And what about the second part? We have IB B1 A2 minus I A1 B2. Okay, so plus I times A2 B1 minus A1 B2. Okay, so once you have this form, okay, now we can separate the real part by the imaginary part. Okay, don't forget that you have a denominator. So it is A1, A2 plus B1, B2 over A2 squared plus B2 squared plus I that multiplies A2, B1 minus A1, B2 over the same stuff, the same denominator, A2 squared plus B2 squared. Okay, so this is the standard form of the ratio. Okay, of course you don't have to learn it by heart. Okay, the important is to understand how to do it. Okay, multiplying numerator and denominator times the complex conjugate. Are you okay with this? Have you got questions about this? Okay, so if you don't have question, I want to be sure that this is okay for you. So a couple of exercises. This. Keeping in mind ratio between two complex numbers, this one. Okay, I want you to compute this ratio, 1 plus I over 1 minus I, and also this other expression, 1 plus I squared plus I over 1 plus I. So try it by yourself. Try to do this couple of exercises just to practice with the ratio, the product of the complex number to time its conjugate and so on. Okay, let me take a look at the chat. We have okay. We are back to the exercises. Are you okay with this? Can I check the solutions? So the first one, I multiply both times the complex conjugate of the denominator. So I get 1 minus I times 1 plus I in the denominator. And as I told you before, this is 1 plus 1. So it's 2 in the denominator. What about the numerator is the square of 1 plus I. Okay, so 1, the square of the first one, negative 1, the square of I, and plus 2I. 2I. So 1, negative 1 cancel out. 2I over 2 is I. Okay, so the solution of the first one is I. Okay, what about the second one? Second one is the square of 1 plus I. We already know that the square of 1 plus I is 2I, plus I is 3I, over 1 plus I, and we have to multiply it times its conjugate. as I told you before, and so the denominator is 2. And what about the numerator is 3i minus I times I is negative 1, so it is plus 3. So let's write it separating the real part, and it is 3/2, plus the imaginary part is still 3/2. So 3/2 plus I times 3/2 is the solution to the second one. Have you got questions on this? Are you there? Can you hear me? Is there anyone? I can't hear you. Are you there?
Clear, Professor.
Okay, thank you. So let's go on. The next step is, okay, let's go back to the geometric representation, okay, that I gave you before. The geometric representation of complex numbers, okay, has another important feature. As I told you, I can represent a complex number z, a plus ib, in the complex plane, where the x-axis is the imaginary axis. Sorry, this is the real axis. I hope to written well before. This is the real axis, and this is the imaginary one. So that any z can be represented as a point or as a vector, where the first component is A, the real part, and the second component is B, the imaginary part. Okay, as I told you, the length of this vector is this modulus, and so on. This representation is also important because it leads to the trigonometric representation. Okay, the trigonometric representation is made up using the modulus, okay, and we will call it rho. So the length of the vector rho, using the Greek letter rho to mean the length of this vector, along with this angle. Okay, so we will use this second kind of representation because it is useful in computing other operations with the complex number, like, for instance, the square. So this is, okay, so the geometric representation leads to the trigonometric representation. Okay, so using polar coordinates. By polar coordinates, I mean rho and theta, the length and the angle. Okay, so rho and theta are linked to A and B within this expression. Rho, we already know that rho, the modulus, is the square root of A squared plus B squared. Okay, and you already know it. You have to recall, okay, you have to recall something of trigonometry. Yeah, okay. So what is the link between A, B, rho, and theta? The link is that A, okay, A is the length of this segment, the green one, okay, So A is given by the product of rho, the length of the vector, times the cosine of theta. So it is rho times the cosine of theta. While B, second component, so the imaginary part of the complex number, is given by rho times the sine of theta. Okay, so these two important relations gives you the trigonometric representation of a complex number. Of course, you can go back and forward between the trigonometric representation and the Cartesian one. Okay, by the Cartesian one, I mean A plus IB. Because if you know rho and theta, you can get A and B using rho times cosine theta, and B is rho times sin theta. If you have A and B, you can find out the cosine of theta. That is, from this expression, is A over rho, and the sine of theta from the second one, and it is B over rho. Okay with this? Have you got questions on this? Okay, these are the two ways of represent the complex numbers in the plane. Okay, let's try to practice with it in a couple of exercises. Okay, so we consider -1. Okay, this is a real number, so it is of course also a complex number, and we want to find out the polar coordinates, so the trigonometric expression for -1. We do the same for a -I, and also for n½ plus square root of 3 over 2 times I, and also for okay, the last one you will find it on the slides. I leave you as an exercise, okay? Because I don't want to waste too much time. Otherwise, we don't have time to end all the topics on the slide. So let's start with -1. How to write -1 using the polar coordinates. Okay, so I think that it can be useful to represent it on the Cartesian plane, the Gauss plane, with the imaginary and the real part. -1 is this one. Okay, so what about rho? Rho is 1, is the length of the vector, while theta is the angle, is this one. So theta is 180 degrees, or pi. Are you okay with this? Okay, you have to recall something about the trigonometric expression. Okay, the angles, it's sine and cosine. So this is 1. Okay, let me write it. I want to write the expression. Z, using this representation, turns out to be A plus AB. Instead of A plus AB, as you know, you can write the polar coordinates. So rho cosine of theta plus I times rho sine of theta. Okay, so collecting rho, you get rho times cosine of theta. So let me write it in another way, otherwise, sorry for this. wanted to write down this, the trigonometric representation of the number z. Since z is a plus ib, we can rewrite it as rho cosine of theta, since a is rho cosine of theta, plus I times rho sine of theta. Are you okay with it? So, by collecting rho, we can write the z, the complex number, as rho times cosine of theta plus I sine of theta. Okay, so we have two different ways of writing down a complex number. The Cartesian one, a plus ib, and the trigonometric one, rho times cosine of theta plus I sine of theta. Are you okay with this? I hope it's clear, even if I wrote it after the other form. Have you got questions on this point? Okay, so in this example, -1, and this is a plus ib. This is the Cartesian representation, a plus ib, where a is -1 and b is 0. Can be written also in this other way, where rho is 1 and theta is pi. So 1 times cosine of pi plus I sine of pi. So cosine of pi plus I sine of pi. Actually, cosine of pi is -1 and sine of pi is 0. So these two expressions are equal to each other. Okay with this? Okay, what about the second one? Second one is this is A and this is B, is -I. -I means no real part, and the imaginary part is -1. So rho is still 1. And what about theta? Theta can be seen as 3/2 pi or minus pi over 2. Okay, it's the same angle. Okay, the same point. Okay, so theta can be seen as minus pi over 2. So rho is still 1, so 1 we can cancel out 1, since it is it doesn't, and it is cosine of -pi over 2 plus I sine of -pi over 2. Are you okay with this? Have you got questions on this? Give me a feedback on this point. Is there anyone?
Yes,
Yeah,
Professor.
all clear.
Okay. Thank you. So next step, another example just to practice with this. Okay, as I told you, you have to recall something about trigonometry. We have to deal with a number that is a plus ib, where a is an half, as and b is square root of 3 over 2. Okay, so square root of 3 over 2, of course you have to recall that this is a known angle. Okay. The angle theta is 60 degrees, so it's pi over 3. Okay, and what about rho? Okay, theta, we have to recall that the sine and cosine of over 3 is 2.5. What about rho? Rho is the square root of 3 over 4 plus 1 over 4, and it's 1. Okay, the point is on the circle whose radius is 1, and it is centered in the origin. So again, is 1 times cosine of pi over 3 plus I times sine of pi over 3. Of course, 1 can be deleted. Okay, so practice with these known angles, okay, and try to recall it using also the last exercise. I leave you, and you'll find it on the slides. Okay, so last important things about complex numbers. The next step is the last representation. Okay, we talked about the Cartesian representation A plus IB, and we passed to the trigonometric representation. Okay, so let me recall these steps. The first one, Z, was A plus IB. Okay, the Cartesian one, Cartesian presentation. The next one, the next step was the trigonometric representation, rho times cosine of theta plus I sine of theta. Okay, the polar representation of trigonometric representation. And the last one that we are going to see now is the exponential representation. Okay, the exponential representation. Okay, before to write down the exponential representation, I want to recall to you the Euler's equation. It's an important relation found out by Euler, okay, the mathematician, the Swiss mathematician, and he found out this relation between the exponential and the cosine and sine. Okay, he found that E, the Nepero number, okay, E, 2.71 and so on, the rational number, to the power of I times theta, where I is the imaginary unit and theta is any real number, is like cosine of theta plus I times sine of theta. Okay, this is an important relation, and in order to prove this, it's enough to consider the Taylor expansion of all the three functions, the exponential, the cosine, and sine. You can also try it by yourself, recalling the Taylor expansion using the derivatives. Okay, it's a matter of analysis of one variable. Comparing these three expressions, you can find out that this relationship holds between the exponential and the cosine and sine function. Okay. By the way, from this relation, we can find out this expression. If we have e to the I times pi, if we replace theta with pi, we have a very famous relation in mathematics. And this is like the cosine of pi, and you know the cosine of pi is -1, so equals -1. Or sometimes you find out written in this way, bringing -1 on the left side, it is e to the I pi plus 1 equals 0. Okay, this is famous relation because it involves many numbers of the mathematics, 0, 1, e, I, and pi, all in the same relation. Okay, so this was just curiosity. By the way, we introduced the Euler equation, and we introduced this equation in order to write down the exponential form of the z of the complex number. So, of course, if cosine plus I sine can be written as e to the power of I theta, the complex number z can be written as rho times e to the power of I theta. And this is called the exponential form. Okay? Are you okay with this? Any questions on this? It's just a definition, of course. Okay, this is just a definition, but along with this definition, we can compute the power. Okay, we can compute the power of a complex number. Okay, so the next step is computing the power of a complex number. So if you don't have questions on this, we go on with the power of a complex number. So the reason why we introduced all this expression for a complex number is that sometimes it's useful to use exponential or trigonometric form. For instance, when we have to compute the power of a complex number, okay, and when you have to compute the power, the Cartesian form is not very useful, okay, because if you consider to compute a plus ib squared, okay, you can even use the, in this case, in this simple case, you can even use also the Cartesian form, and you have the product a times a, so a squared minus b squared, this is the real part, plus I times ab, so 2ab, okay? But, so in this case, it works. But imagine to compute a plus ib, the power of, 17, okay? And you have to compute a plus ab times a plus ab, okay? Times a plus ab times a plus b, okay? 17 times. Okay, so in this case, this form doesn't work. And in this case, it's helpful to use the trigonometric of the exponential form. Okay, and I want to show you how to compute the exponential form introducing the De Moivre formula. But before to introduce the formula, let's see again this product using the trigonometric formula. Rho times cosine theta plus I times sine of theta. Okay. If we do the same using this form, we have, of course, we have rho squared plus cosine of theta plus I sine of theta squared. And this is, I rewrite the rho squared. The power of cosine plus I sine is, as before, as we did here, is cosine squared theta minus sine squared of theta Okay, if you compute the product, the power of the first one plus the power of the second one, but I squared is -1, so this is the power of I sine of theta is negative sine squared of theta. Okay, plus the imaginary part is 2 times sine of theta and cosine of theta. Okay, at this point, if you recall some trigonometric formula, okay, you can recall that this is the cosine of 2 theta. This is a trigonometric formula that gives you cosine of 2 theta is cosine squared of theta minus sine squared of theta. And this is sine of 2 theta. Okay, so I wrote this power of the a plus ib written in trigonometric formula to introduce you the De Moivre formula that I will write in the general form. But this is a particular case where we have rho squared times cosine of 2 theta and plus I sine of 2 theta. And from this, you can argue that when I compute the square of a complex number written in trigonometric form, I get rho squared, so the square of the cosine of 2 theta plus I sine of 2 theta. So the argument, the angle, becomes 2 times the angle of the basic number. So it means that squaring the number means doubling the argument, the angle. Okay, and it holds in general, and this is the De Moivre formula. So the next step is writing down the De Moivre formula in the general form. De Moivre formula. Okay, the De Moivre formula that we will use to compute the power of a complex number. This formula is following z to the n, so the power, the nth power of a complex number is simply the n power of its modulus, rho, times cosine of n times theta, like before it was 2 theta because it was the square, and in this case is the nth power. So r to the n cosine of n theta plus I sine of n theta. And this is the formula we will use to compute the power of a complex number. Okay, and we will use it in an example, but before to use it in the next example, I want to notice that if you write z in the exponential form, you'll find this De Moivre formula in computing z to the n, since z to the n is rho to the n times e to the I theta to the n. And this is like rho to the n times e to the I, this is simply the property of powers, I and theta. And what is I and theta? By the Euler's equation, it is cosine of n theta plus I sine of n theta, as I wrote before. Okay, so this can be a proof of the De Moivre formula using the exponential form. Okay, so this is the formula we will use to compute the power of a complex number, and it is also very useful in the application. So let's try to practice with this formula in an example, just to show you that it is useful also to compute powers with high degree, like 1 plus I to the power power of 20, for instance. How to compute it using the Cartesian form of the number? Okay, it's hard. You have to compute 1 plus I times 1 plus I 20 times. And so if you use the De Moivre formula, you can compute it in a few steps. Of course, the first thing to do is switching to the Cartesian, to the trigonometric form. Okay, so I think you can try by yourself. Okay, let's do it together because we don't have much time. So 1 plus I. First of all, let's switch to the trigonometric form. So we have to find rho, and it is the square root of 1 plus 1. This is the square root of 2. Then we have to find theta. Cosine of theta is 1, the real part, over rho, as I told you before. So it is square root of 2 over 2. And the sine of theta is still 1 over the square root of 2, so square root of 2 over 2. At this point, you have to recall that the angle whose sine and cosine is square root of 2 is 45 degrees. Okay, 45 degrees, or pi over 4. So theta is pi over 4. Rho is square root of 2. And we can write this number in the trigonometric form. So 1 plus I to the power of 20 turns out to be equal to rho square root of 2 times cosine of pi over 4 plus I times sine of pi over 4 to the power of 20. Okay, are you okay with this? So the first step, write this number. Trigonometric form. Once you did it, you have to compute the power, rho, so using the De Moivre formula. Rho to the n, in this case, is square root of 2 to the n, to the power of 20, times cosine of n theta plus I sine of n theta. Okay, cosine of n theta, this case is cosine of 20 times pi over 4. That's I times sine of 20 times pi over 4. Okay? 20 times pi over 4 is an angle. Okay? So, let's talk about this angle. Square root of 2 to the 20 is 2 to the 20 over 2, so it's 2 to the power of 10, okay? Times, this is 20 over 4 is 5, so it is cosine of 5 pi plus I sine of 5 pi. What about 5 pi? It means pi 5 times. 1, 2, 3, 4, 5. Okay, this is 5 pi. Okay, this is 5 pi. So 5 pi is like pi, actually. So its cosine is -1 and its sine is 0. So at last, 1 plus I to the 20 is -2 to the 10. Okay, have you got questions on this? Okay, so
Sorry, Professor.
Yeah.
Why theta is pi over 4 and not pi over 2?
It is pi over 4 since the cosine is square root of 2 over 2, and the sine is square root of 2 over 2. So it has this sine and this cosine, okay, is halfway between 0 and pi over 2. If it was pi over 2, this is pi over 2, its cosine was 0, and the sine was plus 1. While we found the cosine to be square
Okay,
root of
thank
2
you.
over 2 and 2 over 2.
Thank you.
Sine was 1 and the cosine was 0. Are you okay with this?
Yes, Prof.
Okay. So let's go on. We have the last part of this. We have 10 minutes more. Just to show you another important application that you will use during the course of the complex number. So the reason why we are very interested in complex numbers is that using complex number we can solve every algebraic equation. Okay, so or better, we can rewrite every algebraic equation as products of its roots. Okay, so this is stated by the fundamental theorem of algebra. Okay, it states that every algebraic equation, by algebraic equation I mean a polynomial equation, whose degree is n, perhaps better change the, has n solutions in the complex field, so in the set of complex numbers. Okay, of course all solution must be considered with the algebraic multiplicity. Okay, so this means that if you consider the equation x squared minus, sorry, okay, so, let's use this equation as an example of the theorem. Let's consider this 3-degree equation. X to the 3 minus 11x squared plus 40x minus 30. Okay. How many solutions does this equation have? If we look for the solution of this equation in R, you can factorize this using the division with the polynomial or Ruffinus rule, and you will find that a solution of this is 1. Okay, if you replace 1, you get 1 minus 11 plus 40 minus 30 is 0. Okay, this is 0. So one solution is 1. So you can write this x minus 1 times another polynomial. And you can find it using, as I told you before, the division between polynomials. Okay, if you have questions on this, you can ask me during the TA. Okay, it's a basic algebraic issue. Okay, so this is like x minus 1 times x squared minus 10x plus 30. So if you want to factorize this polynomial and look for the solution of this equation, you will find out that x is equal to, but dividing by 2 is minus 10 over negative 2 is 5, plus or minus the square root of what? 5 squared is 25 minus 30. So it's 5 plus or minus the square root of negative 5, okay? And it doesn't exist. It doesn't belong to R. So in R, you can say that this third degree equation has only one solution, okay? So the fundamental theorem of algebra doesn't hold in the set of real numbers. It's not true that every algebraic equation whose degree is n has n solution. In this case, this equation has degree 3 and has just one solution in R. But the fundamental theorem of algebra holds in C, in the set of complex numbers. So if we are working in C, we can go on. At this point, we can go on, okay? Because this is actually 5 plus or minus the square root of negative 1 times the square root of 5. And what about the square root of negative 1? It's a number that squared is equal to negative 1. And this number actually exists in C. Are you okay with this? Okay, it was the starting point for a complex number, which the number such that the square root of its square is negative 1. It was I, because I squared is negative 1. So the solution to this equation exists in C, okay? And we can write that x is 5 plus or minus I times square root of 5, okay? So this second degree equation has solution in C, and it has actually two solutions in C. 5 plus I times square root of 5, and 5 minus I times square root of 5. So we can factorize this polynomial like x minus 1 times x minus 5 plus I times square root of 5 times x minus 5 minus I times square root of 5. Okay, so every nth degree equation, polynomial equation, can be factorized in first degree factors in C, because as the fundamental theorem of algebra states, every algebraic equation whose degree is n has n solution in the complex field. Of course, the solution can have also multiplicity 1, 2, 3, okay? So you can factorize any nth degree equation in the same way I show you, okay? So in order to end this TA, I want to leave you some exercise as homework. You will find them on the factorization. So home, the exercise factorize the following polynomials: z squared minus 6z plus 13. Okay, I use z just to recall you that you have to work in C. Okay, but if I wrote x was the same, x squared minus 6x plus 13, factorize them using the roots. Okay, and also z to the power of 3 minus z squared plus z plus 3. Factorize it. Okay, this is homework. And the next one is solve the equation in 3, and the question is z times absolute value or modulus of z squared minus 4iz squared equals 0. Okay, another homework. Hint, and the hint is collect z and use hints better. Collect z and use the Cartesian form. Okay, and this another homework. And the last one is throw in the Gauss plane. Okay, the Gauss plane was the plane where we represent the complex number with the real part and the imaginary part. Drawing the Gauss plane. Sorry, I think to edit better. Drawing the Gauss plane, this one, the solutions of the following system. And the system is real part of z conjugate times z plus 1 less or equal than 2, and imaginary part of z greater or equal than 0. Okay, so you have to represent this system in the Cartesian plane. Okay, it is actually not an exercise focused on the complex number. Okay, because once you have compute the product of complex numbers and computed the real and the imaginary part, this system turns out to be a system of inequalities in the Cartesian plane. Okay, like x. Okay, you'll find an half plane. Okay, let me give you some hints. You will find the intersection of an half plane and a circle. Okay, using the as you saw during the studying the domains of function of two variables. Okay, so sorry, I am 2 minutes late. Thank you for the attention. See you next Wednesday. Okay, if you have questions, you can ask me.